Happy Friday, everyone. We're going to make this nice and quick and start off with a good bell ringer from yesterday's lesson. So, which element has the following electron configuration? 1s2, 2s2, 2p6, 3s2, 3p5. Hopefully, you are able to say that that is chlorine. And if you draw that out in a Bohr-type model, this is what it should look like. We've got 2 electrons in our first energy level, 2 in our second S, 6 other electrons in our second energy level, 2 S's or 2 S electrons in our third energy level, and then 2, 4, 5 in our p orbital in our third energy level. So today we're going to talk about orbital shapes. This is building very much off of what we talked about yesterday. We're not going to go too into detail about this. If you want a lot more detail, if you want some of the mathematical descriptions, you're welcome to look in your textbook for this. They've got some really good graphical depictions of the things that I'm talking about here. Our learning objective is I can describe the shapes of the s and the p orbitals. Nice and simple. So yesterday we talked about shells, subshells, and orbitals, and we clearly delineated each of those terms. Today it's going to get a little bit muddier because if we think back to the metaphor I used yesterday of the street for the shell, the subshell is the apartment building, and then the orbital is the apartment unit within the building. Each of those subshells, so those apartment buildings, when we look closely at all of those orbitals, all the apartments within those apartment buildings, they've got different unique setups, different unique shapes. So sometimes the line between subshell and orbital seems a little bit muddy because we often use s orbital or p orbital to talk about the different shapes of subshells. It's not too complicated, I promise. But each of those subshells can have different unique orientations. And like I said, we talk about them, or we might label them as the s orbital or the p orbital because of the shape of that particular subshell. And then the shape of, or the subshell determines the shape of the orbital. And then the orbital is that specific area where those 2 electrons might be found or have a higher probability of being found. First, we're going to take a look at the s orbital. The s orbital is always spherical. We can have s orbitals at all the energy levels. In this depiction, you'll notice that the second energy level and the third energy level have something called a node, or 2 nodes in them. So the node is just an area within the orbital where the electron will never be found. Again, this is a good one if you want to see a different depiction of it. Check out your textbooks for the graphical display. But within this sphere, there's areas that the electrons are more likely to be found, and then there's areas where they will never be found, again, within that specific sphere. And those are called the nodes, where the electrons will never be found. So, not terribly complicated, pretty simple, found at all energy levels. And they can only contain 2 electrons max. Our p orbitals get a little funkier. They are called the dumbbell shape, and they can be oriented in space in 3 different ways. Obviously, our spherical s orbital, you turn it, it looks the same every direction. But we can have the, so this is an example of a 2p orbital. So the second energy level's p orbital can be oriented x, y, or z, logically following the graphs and orientation in space. Each p orbital, you'll remember, can contain up to 2 electrons. So because we have 3 different possible orientations, we can have up to 6 electrons in a single p subshell. Now, we're going to talk briefly about the d orbitals because d orbitals obviously get funkier. Ooh, sorry. I do want to go back really quick. The p orbitals, I talked about the nodes in the spherical orbitals. P orbitals obviously have a node as well. Theirs is more clearly defined because it's right where these 2, we call them lobes. this section and this section are the lobes. There are 2 lobes, and where they meet is the node. Pretty simple. Our d orbitals have 4 lobes. You can see 1, 2, 3, 4, and they're going to have 2 nodes then. So one is going to be in between these front and back, and then in between the top and the bottom. There's going to be 2 nodes in each of those. And there are 5 different spatial orientations for d orbitals. Like I said, they obviously get more funky, and each orbital can again contain up to 2. So we have a d subshell can hold up to 10 electrons. We're not going to look at S, but I promise you, if you want to, S gets even funkier. What we are going to discuss briefly is how subshells can be pretty easily seen on our periodic table. So you should have seen something like this before in 7th grade, where you've got your electron configurations written out. And we can actually, there's lots of handy things that we know about the periodic table. And one of them is we can break it up into the different blocks based on valence electrons. So over here, we call this the S block, because all of these have either 1 or 2 valence electrons in their outermost S subshell. Over here, we have the P block, because these have between 1 and 6 electrons in their outer P subshell. Our D block, it follows, and then down here, the lanthanide and actinide series are our F block, and those we don't mess around with a whole lot because they behave strangely. But this is a good thing to be aware of because it can be very helpful when we're talking about electron configuration. Ooh. And finally, your reading assignment is to read chapter 7.1 and 7.2, pages 269 to 282. And if you have any questions, book a time with me during my office hours or send me an email. Have a good weekend.